Okay, welcome, ladies and gentlemen, to the second day of the workshop. Today, we're going to start with a tutorial on time reverse diffusions, which is a very interesting technique in machine learning for generative AI, which has appeared in the last few years by Praneeth Netrapalli. So Praneeth is a research scientist at Google India. He studied, he did his BTech at IIT Mumbai. And then he went to University of Texas, Austin, where he did a master's and PhD in machine learning. And then he worked for a few years at Microsoft Research, first in the US, then in India. And now he's both at Google India and associated with the Tata Institute of Fundamental Research, ICTS, in Bangalore, and also he's associate of TIFR in Mumbai. He has published a lot of very interesting research on the mathematical and practical aspects of machine learning algorithms, ranging from topics related to optimization, and now he's looking at generative AI. And he won the Indian National Science Academy Medal for young scientists in 2021 for this work. So we're very keen to hear his lectures on time reverse diffusion.
Thank you, Rama, for the nice introduction, and thank you, Sandeep, and the organizers for the invitation, including myself. Uh, okay, so the topic for today will be like sampling through diffusion. And if we have time, we'll also look at flow-based generative models. Okay. Okay. So the overall goal is to sample X from some probability distribution P. And there could be different ways in which P could be specified. So one of the settings that's been very widely studied both in theoretical computer science and even in other domains is when X, so P is in particular given as X of minus F, right? And we have access to either F or gradient of F. What I mean here is that if given, so what F means is that we are given Z and we have an oracle which tells us what F of Z is, or we know what Z is, and then, so if we give an input Z, we get grad F of Z, right? So this is one way in which we can say we have access to P, right? Where P is specified as this, and we have access to either a function oracle or a gradient oracle of F, right? Another approach, which we'll primarily be dealing with today, is that we are given samples that are already drawn from P. Right? And then we need to draw fresh samples. Makes sense? So this is the setting that we'll be primarily concerned about in today's lecture. Okay. So I should mention that even when we are given something like this, it is possible to perhaps use these samples to learn an F that to learn the corresponding log probability function, and then use either like the either a function oracle or a gradient oracle, and then use methods that have been designed for this setting to directly apply here. But it turns out that that's not a very popular approach, and practically hasn't had like a lot of success. But today we will be looking at methods which are slightly different, and directly try to take advantage of the samples that are given to us and learn maybe some slightly different kind of functions, which then enable us to actually be able to draw fresh samples from the underlying distribution. Okay. Okay. And in particular, we will be looking at what are called particle-based methods. Okay. So what particle-based methods do is the following. So we have some initial distribution P0, and then we draw X0 from some P0. So let's say this is easy to sample. For example, this could be like a standard normal distribution, right? And then we evolve this X0 according to some SDE like this. The square root 2 here has a particular role, but what this says is that the in any instant of time, like the amount of moment that xt sees is given by a velocity term at xt times the amount of like the time duration dt, and then we have a sigma t times a Brownian motion. So I'll not explain like all the properties of Brownian motion, but we will only give like the main properties of Brownian motion that we will use, which will be basically captured by Ito's lemma. So we will state that in a little bit, but apart from that, we will not be using any other properties except for Ito's lemma. Okay. Yeah. Yeah, I'll spell out Ito's lemma in a little bit. Yeah. Okay. Yeah. So the overall goal of these particle-based methods is that we want to choose an appropriate V and appropriate sigma, so that when we start from whatever initial distribution and then we let it evolve according to this, after some time, the distribution of xt will eventually be close to that of the target probability distribution p, right? So the question is, how do we find a vt, and how do we find like the sigma t, so that when we do this evolution, the eventual distribution that this converges to is the target distribution p. Okay. Yeah. P naught is just the initial distribution. Yeah, P naught will transform. So actually, that's a very important point. So yeah, so that's one of the main things we will do in a little bit. So this is in the particle, like this is in the path space. So we have a particle and the particle is moving, right? This corresponds to a movement in the probability distribution space, right? So how does this translate into the corresponding probability distribution movement is one of the things that we'll prove in the next little bit. Yeah. 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 I mean, here right now it does not. Yeah, these are simpler class of uh, yeah, particle based methods, and usually like these are the ones that are used most in practice. I think like Markov chain Monte Carlo is closely related to Langevin dynamics, right? So that's one of the things that we will cover. So it is probably closely related, but I think the main idea here is probably complementary to it. Maybe at the end of the lecture, maybe we can revisit that question. Any other questions? Okay, so the main thing that we want to do here, okay, so the first step in even understanding how to think about this is to understand what does this particle flow here correspond to in the space of probability measures. So if x0 comes from p0, xt will say come from some let's say pt denotes the probability distribution of xt. So how is pt evolving from p0 to the eventual target distribution, right? So in order to write that, we need a few definitions. So okay. So we say that two functions f and g are equal if so for every test function phi in CC infinity of RD, what this means is that phi is compactly supported, meaning that it is non-zero only in a bounded and closed on a bounded and closed set, and it's infinitely differentiable, right? And all the derivatives are also compactly supported because the function itself is compactly supported. Okay, this makes sense. So we are saying that f and g are equal if for every test function, the integral of phi and phi times f is the same as the integral of phi times phi. So we now state Ito's lemma, and this is the pretty much the only property of Brownian motion that we will use. So Ito's lemma basically tells us that if we are given a stochastic process xt, which could have some Brownian motion components inside of it, and then any function phi, which depends on both the time step t as well as xt here, the time derivative of the function phi is given by the partial derivative of phi with respect to t, right? Plus the gradient with respect to x phi of t comma xt and then dxt plus sorry, phi times multiplying. with the convention that dt square equal to 0 and this is equal to dt times dbt, let's say I, and this is also equal to dbti dbtj for I not equal to j. This is equal. Any questions on this? Yeah. I mean, dxt, we haven't explicitly said what the form is. This is just generic, right? Dxt can, it will have some dt component and some db component, and there could be interrelations as well. I mean, yeah. All this is saying is like Brownian motions, which are like the same Brownian motion, if you multiply them, we'll get a dt, and different Brownian motions or Brownian motion with time or time square, all of them are equal to 0. So, sorry, sir, thanks. Okay. Okay. So this is the first main result that we want to prove, which is, which basically says what is the probability evolution equation for a given diffusion equation. Okay. So if xt evolves as x0 comes from p0 and dxt equal to vt of xt dt, then del tpt can people see here? It's not visible. Can see until here. I need to write bigger. Okay. Is this okay? Okay. Oh, okay. So does the statement here make sense? So if xt evolves according to, okay, so where pt is the distribution of xt. So if xt evolves according to this equation, vxt is equal to vt of xt dt plus square root sigma t, square root 2 sigma t dbt, then let's look at the probability distribution of xt. Let's denote it by pt. Then pt evolves according to this equation. So del t pt is minus grad dot vt pt. So this is the divergence operator. So the divergence operator, is it, I should not write here. Okay. It's okay. Okay, so notation. So grad dot g is given by summation I equal to 1 to d del gi of x divided by del x, where g maps rd to rd. Any question about the equation and what this means? Sorry? Oh, this one. Ah, okay. So this is the Laplacian operator. Yeah, it's the density. Pt is the density from which xt is being drawn. So Pt is a density. Because Pt is a density, it's a function that takes Rd to R, right? So that's how we look up Pt. So that's why we can apply this Laplacian on Pt, right? And Pt is again a scalar function. Bt is a vector function. So at every point you have a velocity field, which is again telling it how to move. So it's a function from Rd to Rd. At every point in the space, it's saying like in which direction you should be moving. And then Vt times Pt is again a vector function, like because Pt is a scalar, right? So this entire thing is a vector function, and then we are taking divergence of this product here. Think it probably goes by many names. I think of it as maybe the continuity equation. Yeah. Like for the diffusion models, this is the Fokker-Planck equation. Yeah. Yeah, there is a dt. I guess, yeah. So if you take the partial derivative, so yeah. Yeah. I mean, we're taking it to be a scalar here, but we can generalize it to the matrix setting also. Yeah. Okay. So the reason why this is important is this tells us what this tells us how the probability distribution evolves. And because we want to ensure that the final probability distribution is going to be our target distribution, this will make it easier for us to verify under what conditions on Vt will our P star be the invariant distribution. Like firstly, like the target distribution has to be invariant, right? Because we keep on running this, then we should not move from the target distribution. So firstly, it has to be an invariant distribution of this equation, right? And yeah, then you should not move from there. Yeah, yeah, yeah. So that's why this probability evaluation equation is important. And now that we have, I mean, we need to prove this. So that's what we will do now. But assuming that we are able to prove this equivalence, then that will tell us how exactly, like what kind of VT might actually enable us to reach the target distribution. Okay. Okay, so now we will try to prove this equation. And again, the two main tools that we will use are only these two, right? So we'll use the weak equality of functions, and then we will use Ito's lemma, and then we will try to prove them. So is it okay if I use that board, or okay? Yeah, I think it might be. Can people see here? No. Is it possible to maybe get the screen off? Maybe I can use that part of the board. No, they might be able to see here, but not here, I think. Can people see here? No, not here. Okay, so let me try writing from here. If people don't see, let me know. Okay. Okay, so we want to use the definition for the weak equality of function. So let's consider any test function. Right? And what this means is that there exists T0 and T1 such that phi of s comma dot is equal to 0 for every s. Okay, and also yeah, maybe I think like this is the main thing. Okay, so because of this, right? So we have phi which is compactly supported, and we are integrating how it varies across like from 0 to infinity. And because phi is compactly supported, it can have any variation only between t1 and t2, right? And beyond them, it's anyway equal to 0. So this entire integral will be equal to 0. Yeah. Because of lighting, or it's not. Is this better? Okay, so let me maybe just stick to that side of the book. I don't know, like it depends.